So hi everyone, my name is Rand. I'm the co-founder with Pascal here of Zama. We're working on open source homomorphic encryption. We've been organizing those meetups for a little bit over a year now to bring the community together. And we're getting close to a couple thousand people now, which is amazing. We also have a Discord, in case you haven't joined it already, where we talk about all things homomorphic encryption. Just before we get started, I want also to ask the community if they would be interested in helping us at Zama break our concrete framework. There has been a few side channel attacks published recently on other frameworks, and we'd like to see whether we can actually attack our framework as well. Short answer is 100% sure that we can. And then find mitigation strategies. So this is an important topic. So if you're interested in side channel attacks and want to contribute and help us, make this more secure, publish papers around it and everything, please get in touch and we can start working on that. So coming back to TFHE.org. So today we have a very interesting session around zero knowledge proofs and verifiable computing for not just for homomorphic encryption, I guess, but also for homomorphic encryption. And Anca here is going to be the presenter. So Anca works at a company called Protocol Labs, which is a great company behind protocols such as IPFS, Filecoin. So Anca, I'll let you introduce yourself, but needless to say that you're one of the experts in zero knowledge proofs, and I'm personally very excited to hear what you're going to be talking about.
Okay, thanks for the invitation. I'm super happy to talk today and kind of bridge the communities between TFHE and zero knowledge proofs. So as Jan said, I'm at Protocol Labs. I'm mostly working on protocol for distributed storage and proof of storage. This implies a lot of zero knowledge proofs, SNARKs, and vector commitments. And today I will talk about verifiable computation over encrypted data. So let me start sharing my screen. Okay. This is about a setting where we have a client that wants to delegate their storage because many reasons, right? We have small devices as clients with limited storage, minimal operation system. We don't have a lot of computation power, so usually we delegate all this stuff to external servers. So here is our client Alice. That will just use some cloud services or distributed systems for storage and for the computation power that allows to do some sophisticated computation on their data. Of course, there are many other things that we can consider, like network services, software, or other outsourced things. So in this setting, we have the following scenario. The user, Alice, delegates its personal data. It forgets about it and it leaves the server to store the data. And later on, it probably would like to compute some algorithm on their data and just find out the results. So the server will send back the claimed result of some important computation. And the user just has to read the result and trust that that's correct. So, okay, we are a cryptographer and usually we don't have this notion of trust. So what can go wrong in these scenarios? So the data Alice delegates to some server, it's completely exposed. It can be stolen, it can be used in any other unwanted scopes. So the best, it's not to trust the server about the data. And this is why we have encryption, and even more, we have homomorphic encryption or fully homomorphic encryption that allows not only to hide the inputs, to hide the personal data, but also enables computations on this ciphertext. So Alice can encrypt the data with this fully homomorphic scheme and then ask for the server to do computation on encrypted data. And hopefully we have many schemes, and here it's just a few of them, that allow us to do fully homomorphic encryption with privacy for inputs and malleability for data. And the other side of untrustfulness, it comes from, what about a dishonest server? Okay, maybe the server is not curious about the data itself, but it's willing to save some work and not perform the computation correctly, or just maliciously modify the computation. So how can we protect Alice from a server that is corrupted, in the sense that here is the data, but here we have somebody in control of the data, maybe somebody like notorious for dishonesty, like Pinocchio. And Pinocchio, instead of sending the real computation, will just lie about the results and send something else, y prime here instead of y, for example. And this can have serious outcomes, like, for example, Alice doing something wrong or something that makes her small here. Okay, so incorrect results can appear, and this is a line of works that that treats this kind of solutions, which is called verifiable computation, and allows the server, the Pinocchio here, to prove the correctness of a result. So with respect to some computation. So Alice can ask more than just the result of a computation, can ask a proof that all the computation was performed correctly. And we have a bunch of schemes known as SNARKs that allow this kind of proofs in a succinct way, where the proof has a size independent of the computation it needs to show. We also require that this interaction between prover and verifier should be minimal. So in SNARKs, the prover will just show a small proof and nothing more, will not interact with the verifier, with Alice here. And also we ask for Alice to be like very efficient in verification, more efficient than just computing by herself all the computation again and check the correctness. And in this area of research, there is a long line of works as well, and it continues with more recent works that allow for construction of SNARKs with better efficiency and better performance. But what we really don't have, we don't have this combination of two properties, privacy together with verifiability. So what we call verifiable computation on encrypted data. There were a line of works on FHE that optimizes FHE as much as possible. And there is a line of works on verifiable computation that optimizes this as much as possible. But unfortunately, they are kind of incompatible because they don't account for the same kind of setting or the same kind of arithmetics behind. And this is a really open question and open research direction. So what we really want is that Alice encrypts the data, delegates it to the server, because FHE allows evaluation on ciphertexts, on this encrypted data. The server will compute things, will compute an algorithm, but on ciphertext. And we need a proving system, like a verifiable computation, that allows to show correctness of a computation that is made on this ciphertext. So it has to support the algebraic structure of ciphertext. And then Alice can just use her secret key, like decrypt the result of the computation, and not only, also check this proof on top of the computation in order to validate if the result is correct or not. So that will be the ideal solution. And let's see what are the challenges and why verifiable computation via SNARKs, as we have them today, are not accounting for this kind of situation, or the scenario where we have encrypted data. Okay, so I will present you some recent or more old work of mine on this kind of direction of improving verifiable computation with privacy. And one of the works was treating computation over encrypted data that goes beyond linear computation or quadratic computation and goes to any polynomials, and has privacy not only for the inputs, but also for the outputs of the computation with respect to the verifier, and the verification is public. And this was a work of Dario, myself, and David from 2020. We have other kind of more precise, more tailored verification for encrypted data for specific scenarios. So it's not any kind of computation, but really, for example, here we worked on private polynomial evaluation. So where we have two users that want to compute the evaluation of a polynomial in a point with hiding the point and hiding the polynomial. And we use TFHE for this. And the SNARK we need to prove correctness of the evaluations that happen in this protocol are really tailored for polynomial evaluation and nothing more. So this is a recent work of Malika, myself, Paola, and David on oblivious polynomial evaluation with malicious security. I will briefly mention this also. And what we will focus today is a work of mine on SNARKs that are compatible with the structure of TFHE ciphertext, but not only. There are SNARKs designed for any ring arithmetics. And since TFHE ciphertexts are rings, some LWE rings, this can also apply to this kind of computation over ciphertext. Okay, so let's see what is the outline for today. I'll start with some background on SNARKs in general, give the framework that we need for Rinocchio, which is like the contribution is more, we give a framework to construct SNARKs for any ring, and then picking the ring we need. So for example, a ring for TFHE, we will have to instantiate this framework with specific tools so that this becomes efficient. And then I will show about, I will just mention the challenges and how we invented new tools and we define new stuff in order to make SNARKs over rings possible. And we will conclude together with open questions. So let's start with SNARKs in general and what's the background in order to understand how SNARKs work and how we can improve them to make them even more expressive and apply them to encryption. Okay, so we have this verifier, Alice, and the prover, Pinocchio. And the prover will try to convince Alice of some claim, of some computation over some data. And the algorithms to do so are a setup algorithm that will generate some common reference string, so some public setup that we need further in the protocol. And usually, because we want zero knowledge in general, we will have a trapdoor to this public setup, and the trapdoor should be like thrown away after the setup is done. Okay, we have a proving algorithm that takes the CRS, which is public, and the function we want to prove, a statement X, and the witness, so all the transcript of the computation of f of x, and proves that f of x was evaluated correct. And here, X can contain also the output. Let's say that the relation we want to prove is that f of x and the witness, all the intermediate values in this computation is 1. And the witness will be kept secret if we have zero knowledge. And we have a verify algorithm that takes the same public CRS, not always. Sometimes we need a secret key for the verifier. I will mention this later. Takes the statement, so f evaluated in x, will be 1, and the proof, and we'll check if the proof is correct with respect to the statement or not. Okay, and what are the properties that we want from this proof system? So a proof system with these 3 algorithms, in order to be a SNARK first, a succinct non-interactive argument, is required to be succinct. So the proofs should be independent of this witness size, and the witness is usually the transcript of all the computation we need to do. So it should be independent. It should be non-interactive in the sense like prover and verifier should not exchange other messages in order to verify. And it should be an argument, meaning that we will not expect it to be sound against any prover, but against computationally bounded provers. So we model the adversary as an adversary that has a maximum computation power, and with this adversary would not be able to break the scheme. Okay, and in order to have a SNARK, we need something more strong about the soundness. We need knowledge soundness, and knowledge soundness is a property that says that the prover not only shows that this statement is correct, that this is the result of a computation, but knows all the transcript of the computation. So it performed the computation itself. And this is modeled definitionally as a witness that can be efficiently extracted from the code of the prover. So the prover really used a witness in order to prove the statement. And we can add zero knowledge, which is usually coming for free. It's just a re-randomization of the proof in order to hide this witness. So if we don't want to reveal more than the fact that we know a witness for this statement and what the witness is to the verifier, we can keep secret all our sensitive information that we use in the computation. So the prover doesn't reveal more than the correctness of the statement to the verifier. Okay. And next, I would like to show you a little bit the landscape of the SNARKs with constant size proofs, which all of them require pre-processing. So we have some older schemes here that use some quadratic span program and quadratic arithmetic program in order to design SNARKs. And I will explain more today what are those programs. We have a more generalized version of this kind of SNARKs via linear interactive proofs, as they were called. And we have the state of the art, actually, the shortest proofs SNARK, which is by Grod 16. And all these SNARKs has this particular property that ahead of time, the prover and the verifier have like a pre-processed information, this CRS, this setup that is trusted, or if we don't need zero knowledge, generated by the verifier. And then we can prove using this trusted setup, and the proofs are constant size for these constructions. And this is the kind of property that we need and we focus on for building SNARKs for encryption, computation over encrypted data. Okay, so just to continue into the background, but also enter a little bit the framework for Rinocchio, I will show how SNARKs are constructed in the literature. All these SNARKs with constant size proofs, they have kind of a common blueprint, and we exploit this blueprint. We generalize it to work also for the rings, and at some point there are some challenges, so we need to change some of the things. So what we really do in SNARKs, we take the computation and we translate it into a program that is algebraically friendly in order to make succinct proofs here. So this program is something like a problem to solve on polynomials. So it's a new problem to solve, and the prover has to show us that they have a solution of this problem. Okay, let's go more like into how such a program will be constructed. So in order to prove a computation in SNARKs, we model it as a circuit satisfiability problem. So we have to write this computation f of x equals y as a circuit that takes inputs x and y and outputs 0 or 1. Okay, if the statement is true, it usually outputs always 1. Okay, and the prover just has to show that it knows all the intermediate wire assignments such that this circuit is satisfiable. Okay, and a witness for such a circuit is really sending all the intermediate wire values, which is not succinct. So it will be as long for Alice to verify it as recomputing the proof herself, probably. So that's a trivial solution, and it doesn't help in the outsource of the computation setting. So instead of this, we will try to translate this problem into another equivalent problem such that the prover can do something smarter and send something smaller. So what we will do, we'll take the circuit and we will translate it into this polynomial problem. Here it's like just a pedagogically taught example where we have two polynomials, v of x and t of x. And what the prover needs to find it's a new polynomial p of x such that p of x times t of x equals v of x. What does it mean? It means it has to demonstrate that t of x divides v of x, for example. Okay. So demonstrating this is computing a quotient, and the quotient is p of x. And demonstrating to the verifier that it knows the polynomial p of x can be as simple as that, just sending all the coefficients of this polynomial. But unfortunately, the way we encode the circuit into a polynomial problem requires that the polynomial is as long as all the witness for the circuit satisfiability. So it doesn't help you either with the succinctness to send the polynomial. It's as long as the witness. And this makes sense because the two problems are equivalent, solving the system or solving the polynomial problem or solving the satisfiability of the circuit. Okay, so we need to do something smarter, but we have polynomials, and polynomials have nice properties. And one of the property of the polynomials is that if we evaluate the polynomial in the random point, this kind of equation on polynomial evaluating that point should still hold, and that can be a proof. So if we ask the prover just to evaluate the polynomial in a random point, that should show that they know the polynomial, if they have no control of that point, of course. So sending a proof that is just the evaluation in one point goes from all the coefficients of a polynomial to a single value, which is succinct. So it solves this problem. But it doesn't solve the soundness because, as I said, if the prover has the choice of the point and it can pick it by itself, it can always cheat here. It evaluates everything in that point and then sends a value instead of a real polynomial evaluated in the point. So we will do something to prevent the prover from controlling the point. We will encode the point in such a way in this setup, such a way the prover cannot know what the point of evaluation is, but will still be able to evaluate the polynomial in the point. So we need an encoding with nice properties such that the new proof will be an encoding of P evaluated in S, where P is the polynomial of the proof. So now the proof is just an encoding of P of S. And why this is a proof? As I said, we have the same properties on the evaluation of the polynomial in some point, and the verifier here should be able, knowing V and T, which are given, they are public, should be able also to evaluate in this hidden point from the setup, the polynomials T and V, and check the equation here. Okay, so it seems like we have a solution for how to construct SNARKs. We just need to find an encoding that has all these properties. First, Rinocchio here needs to see only an encoding of some secret point, be able to compute the encoding of his polynomial evaluated in those points, and Alice here should be able to check a quadratic equation here between encodings, right, with respect to some known coefficients. So we will ask for these encodings to have some properties, and even more, we will send more than just the encoding of a single secret point S. We will send all the consecutive powers up to the degree of the polynomial that the prover has to demonstrate knowledge of. So it has to demonstrate that it knows a polynomial P of degree D. So we send them all the powers up to D. So it can then linearly compute. If this encoding is linear, then it just does a linear combination of the encoded powers with the coefficient of the polynomial P, and that will give a valid encoding of an evaluation of the polynomial. So we have a linear homomorphic property that allows to compute encoding of the polynomial evaluation like this. Okay. And we need something more for the verifier. So the verifier should be able to take this encoded value to encode by itself T evaluated in S with the same linear homomorphic property, and check a quadratic equation here. So this it's called quadratic root detection, which means that it needs to check if this equation here has roots in S, right? Without necessarily opening the encoding. Encoding needs to have this property, like allow the verified ring. And image verification is something like if it receives an encoding, the verifier can be able to say, is this a correct encoding of something or not? It's in the image of all the possible encoding or not. Okay, so we had a bit of the blueprint and the way to make SNARKs for different computation is always following this blueprint, but with different kind of computational model representation with different kind of encodings. So these two ingredients change all the time. So we have the statement, as we say, this relation to be proven, which can be an arithmetic secret satisfiability, as I said in the example, and a way to encode such a system is either by quadratic arithmetic programs or by square arithmetic programs. There are two models, and they are all programs like polynomial problems that are defined over a field. So polynomial should be evaluated over a field. And those are the assumptions behind. I will not get into details about the assumption, it's more theory details here. And if we have a Boolean secret satisfiability, we had different way to compute this representation, these programs, and those are quadratic span programs or square span programs, but they are also defined over a field. So this is the way you define them. And what we really need is, what about if we don't want to go and encode our computation into arithmetic secret over a field or a Boolean secret over 0 and 1, and we want just to perform perform computation over rings themselves, which don't look like that. If you have any question till now, maybe I can stop and take some questions. Let me know. No? Okay. So I can go further and see how we can deal with this problem that everything right now, it can be encoded only in an arithmetic secret or a Boolean secret. And what we really want to treat is computation over rings. So here we have a ring of polynomial, let's say, and we want to do a program over this one in order to allow for succinct proofs. So what we know how to do is to take a secret over a field and to do, like I said, and to do SNARKs, but we would like to translate this one. And this translation is, if we are ready to rewrite all the gates, it's really costly. So rewriting all the gates means treating these polynomials as their coefficient and write all the polynomial additions as field additions. Like in terms of their coefficient and polynomial multiplication, it becomes really messy because multiplying the coefficients of two polynomials, it's like a convolution of two vectors. So this is some numbers I have for how this will translate in field gates, in gates over field elements. Will be asymptotic n times d of scalar additions, and m, where m is the number of multiplication the gates, times d, where is the degree of the polynomial, log d multiplication, with the best algorithms that we know for multiplication of polynomials. Okay, so we need a better solution, and we need something that will not just translate everything into arithmetic secret, and we'll treat general secrets over rings into a new kind of program. And this program is quadratic ring program over any kind of ring R that we will be able to instantiate with our needed ring later. And yeah, this is new assumptions, which is not so surprising, that follows exactly the pattern of the ones before. So contribution for short for Rinocchio work, it's taking one of the most efficient like SNARK construction and try to readapt and redefine everything in order to make it work over rings instead of fields. And this will unlock a broad number of applications. And those that we had in mind when we started working on this was outsourcing computation on encrypted data, as I presented at the beginning, but not only anonymous credentials which work over RSA groups, so not over fields, these composite order groups, and machine learning that operates on CPU kind of architecture, and this is not the usual field. It's set to the K. Okay. So we will use our new construction to instantiate with different rings in order to make it work. Okay. And now more technical details on how we construct SNARKs over rings. And this follows kind of the same blueprint where we need a new ring representation for circuit satisfiability, where the circuit works over rings. And we need new encoding schemes that can encode rings, not only fields. And that's something challenges. And here we have a lot of different open direction because we didn't think of many instantiation. We give mostly the framework. Okay, so I will go into these couples of slides. Are not really necessary to follow the rest of the talk, but for those who are interested of how this encoding works from some computation to quadratic ring program or to any quadratic program, I'll show you in a small example. So if we want to prove to someone that we have a solution to this equation, ax squared plus c equals 0, we will write it as a circuit in this manner. Here is x, the value we want to show that satisfy this equation. And here are the wires assignment of the circuits. Okay, and we have a system where each output of a gate can be written in terms of the inputs, right? A times x, then z2 is z1 here, that with x, and the output of the last gate, so the output of the entire computation is c plus z2 times 1, just because the last gate should always be multiplicative in order to account it in this kind of encoding. And of course, if we look a little bit closer what this means, if all the these are satisfied, and indeed this last output is equal to 0, we have exactly that c plus a times x squared equals 0. So we have just to show that the output is 0 here on this system. Okay, so we show that we have assignments for all these wires that satisfy this system of equation. And we can rewrite this system in terms of some vector A that accounts for all the variables here. One is just the constant because we need a constant. X is one of the variables as Z1, Z2, and the output are these other variables. And I've written the thing here for each equation, for each of these lines, we have a way to write it as inner product between vectors times another inner product between some vector and A equals the resulting vector, the resulting inner product. So here we just take A and put it in the first position. Here we have to select X to have AX. So yeah, here A is from the first position times 1. And here the second position is just X. So we have AX equals, and here we have to select Z1, and Z1 is the third position. So we multiply with this. And we do the same for each free equation. And if we look at only this part here, we can write it as a matrix times the vector A, right? And here the same. But between these matrices, there is a pairwise product here, because we need the first element from here to be multiplied with the first element from here. So it's not a matrix multiplication, it's a pairwise between these two, matrix times vector. And here is the matrix defined by the three vectors here that select the element in the A and the A vector. Okay, so this is how we translate things from a system of equation into a Hadamard product between matrices. And going further, we can see these matrices by interpolating each of their elements into some random point R here from the field, in the ring case from the ring. We interpolate them and we write all this matrix times vector as a linear combination with the vector coefficient of polynomials, VIs in X. Okay, and these are polynomials of degree D. And we have M of them. Have V1 here, V2, V until Vm, and we interpolate in D different points. So we define a polynomial. And this is satisfied if in all the interpolation points, this equation, polynomial equation, evaluated in all R's is 0. So it means that this polynomial here should have roots in all R's, all the values R's. So it should be a multiple of the polynomial that is defined to have roots only in the R's, or the polynomial of degree D that has roots exactly in the points R. Okay, so that's the quadratic arithmetic program, and we have to do some change in order to make it over a ring. Okay. So let's see more closely what doesn't work for rings. So we have this target polynomial, what we call, that is defined by the random points where we interpolate it. And if these points come from a ring, unfortunately, this polynomial here, this T of X, when we do the quotient from the initial ring with this T of X, this quotient ring here, it's not necessarily congruent with the product of these different quotient rings over ideals. So each ideal is defined by X minus one random element from the ring. So those ideals in the field case are coprime. So this kind of Chinese remainder theorem holds in that setting when the ring is R is a field. They are all coprime, and we have this equivalence. For any polynomial in this quotient ring, we can write an equivalent vector of polynomials in these different ideals that are coprime. And this is also isomorphic with some of their evaluation in the random points, the evaluation of this point. So these different structures here are all isomorphic when it comes to field. This is not true when it comes to ring. So this will not preserve soundness with respect to the original computation that I shown over the circuit. So what do we need to solve this? We need to see what's the same kind of properties from these ideas, and that are done by choosing the elements for the interpolating of the polynomials from something that we call exceptional sets. And they are sets because they don't have any group structure. They are not even closure. So if we take two elements in the set and we add them together with the operation of the ring, we can get out of the set. We can get an element that is not even in the set. So it's really a set. It's nothing more than a set. And it has this property that any difference of two, like the subtraction of any two elements from the set, should be an invertible element of the ring. And if we define such a set A in such a way, the ideals constructed by using only elements from the set, so if we choose all the randomness for interpolating from the set, we will end up with ideals that are coprime, which is great, which is exactly the field case. And this is something that we need to to make sure that exists for any ring where we want to define SNARKs. And this is possible because we can do like a Galois extension of rings, and we have a bunch of very mathematical tools in our paper, but I will not go into details here. So yeah, it's the only technical part I wanted to show, that once we have elements from this exceptional set, we can make sure that everything works as in a field. And we also have the same Schwarz-Zipper lemma over rings, given that we always choose our randomness here from the exceptional set. So this says that the probability that a polynomial evaluated on a random point S from this, where S is chosen from the exceptional set, would be 0. It's maximum the degree of polynomial over the size of the exceptional set, which is why we need big exceptional set. Okay. And further on, I wanted to talk about the encodings. And what do we need about these encodings? So I said we need something linearly homomorphic, so we can add together, we can do linear combination in order to evaluate the polynomial in the encoded, in the encoding. And we need something more. We need to be extractable, and that's just a way to say that once we are given a set of encodings for some, the only way to create new encodings is to do a linear combination of the given ones. And this means that we can extract the coefficient of this linear combination from the prover. And in encodings, in general, we ensure this property by just asking for the prover to double its effort with respect to some secret factor alpha. So if we ask the prover not only to give us an encoding of a new element P, but also together with the encoding of alpha P, then this means that without knowing alpha, it will never be able. But in a single way is by choosing a linear combination of the first set of encoding they get and the same linear combination applied to the second set of encoding, and then it will be sure that it gets the two encoding set. So we can extract. We know that the prover, if the prover can do this, we know that they must have used some coefficients and some linear combination of those. And this is what we need from encodings. And over fields, we have nice encodings over discrete log groups where we hide the values in the exponent. So an encoding of some value S is G to the S, where discrete log is hard to solve. So we cannot just recover S by looking at G to the S. In the more general setting where we don't have fields and we have any kind of messages M that we want to encode, this can be done by some encryption scheme. And the encryption scheme that is linearly homomorphic. So we can do linear homomorphic operation over the encryption, and then the same thing can be modeled with the encryption scheme. What's the disadvantage? Is that we really needed the verifier to check some quadratic operation, quadratic property between encoded elements. And in the field, we can do it by using bilinear maps over some groups, where we can check some quadratic thing in the exponent. So we can, if we want to check that this value times this value equals some P of S value, we will apply bilinear maps over this. This will be exactly equivalent with E, G, G, and T times H, and we can just check if it's equivalent with this one. While in the encryption scheme encoding, the only way to do this, or as far as I know, maybe there are smarter ways, is just to give the secret key to the verifier. And the verifier will just get out the ciphertext and see the plain text and see if they satisfy this quadratic operation. So that's the disadvantage of using encryption schemes as encoding. And over rings, we are not really aware for any ring in general. For some rings, we are aware of some bilinear map property like that, but not over generic rings. So what we were thinking in order to encode LW-like rings, in order to instantiate Rinocchio over this. So we were thinking of encoding with TFHE because we need to encode this kind of rings that are rings of quotients of polynomials. And using TFHE probably can work, and only using the linear homomorphic property of TFHE. So a very rudimental version of TFHE where we don't give away information for bootstrap or nothing. And also this will allow us to pick any modulo here, Q, which is a product of primes. And the exceptional set size will be the smallest prime size here. So the smallest prime should be still big in order to have some soundness. Okay, so what's important is that this is the first SNARK to support rings with Q that is different from prime. All the others before were treating some kind of rings, but with Q prime. And allows for significantly better choices of LWE parameters if we account from scheme as BGV or FV. The scheme is only designated verifiable because it uses, but of course, if we find better encodings, we can go to publicly verifiable. It's the fact that the encoding is the encryption scheme. And anything that is bootstrapping operation, we don't know how to model as a secret with addition and multiplication gates over rings. So we need to find a way to model bootstrapping of some FHE in an algebra, in a ring arithmetics manner, right? Okay. So here are some parameters that we were thinking that are good for instantiating BGV and FV. So we will need to find an encoding scheme. I don't know if TFHE is practical enough for encoding this size of parameters. So L here is the level of the, because we cannot do bootstrap, we will have a leveled scheme that allows for this kind of levels of computation. N is the degree of the quotient polynomial, H here. And P1 is the smallest prime here, and Q is the overall modulo. So those are some parameters, and I'll be happy to have the opinion of the experts in TFHE if they are feasible in order to encode RQ elements in such a way. Okay, so I will present now some other approaches really fast. So we have this 2020 paper on bootstrapping verifiable computation over encryption data that also treats secrets over rings, but only over rings RQ with Q prime, where these are polynomial over ZQ modulo some other polynomial. And the idea is to go from secret over rings back to secret over fields, apply a known SNARK, and to demonstrate that this bridge before ring, the secret over ring and the secret over field, it's done correctly. So there is a link between, and then just prove the thing over the field. So how it works, we have a secret over polynomials, and these are polynomial equation. And what we will do, we will commit to all the inputs here, and we will evaluate them in point K, and show that this secret is equivalent to this when we evaluated all the polynomials in a secret point K. So multi-evaluation of all different polynomials in the same point K will give us a secret over scalars, and we can prove that this evaluation is correct using some sigma proof, which is the contribution of our paper, and then recombine the commitments that we have here with the SNARK over field, and be sure that sigma together with the SNARK shows that the entire computation over polynomials is also correct. Okay, so this gives us also commit and proof kind of SNARKs, which is a little bit more modular. They are publicly verifiable in the sense that not only the person that decrypts can verify and who has a secret key, anyone can verify that the ciphertext was generated correctly with respect to the initial data, which was encrypted. And there are zero knowledge for inputs and for the computation. Okay. And the other work I wanted to mention briefly is the dedicated to some two-party computation SNARKs, which uses minimal interaction because it uses FHE. So this kind of FHE scheme is used for oblivious polynomial evaluation, which has also application to private set intersection, or is PSI here. And what was the problem here? We have a receiver that has a secret point A, a sender that has a secret polynomial, pi x to the I, and the receiver needs to find out the evaluation of the polynomial if in the point A. So what we will do, it will compute ciphertext of powers of AI, as many as the communication will allow for. So if it wants to have minimal communication, it will just send C to the A. If you want some trade-off between the sender's computation and the communication, it will send many powers, like, and then the sender will compute the remaining ones, and it will apply inner product between the ciphertext of the powers and the coefficients of the polynomial in order to evaluate the polynomial homomorphically in the point A. So it needs all the powers here. Okay. And it proves that this evaluation over ciphertext, because everything is done over ciphertext with PI, which are in clear, is correct via pi. And the receiver will have to just decrypt C of P and look at pi and see if that was done correctly. So this is the SNARK needed here is only for inner product over encrypted vectors. And encrypted vectors of consecutive powers. So it's very specific computation, and we optimize everything to work for this use case. Okay, so I think I'm at the end of my talk, and the conclusion will be that yes, there is a lot to do more, but this was the first work on quadratic programs over rings that leads to a framework to construct SNARKs once we choose an encoding. And as I said, we also show how to design circuits for special operation FHE, like modular switching. We have arithmetics for RQ, where Q is not a prime always, but it's designated verifiable only because we do it by just encrypting this kind of elements. And also we don't go into details of how to do the full zero knowledge transformation, but this is also something we can do with, that depends on the encoding and the properties of encoding. And if we use some FHE, then we need context hiding techniques in order to hide things there. So open questions will be, what other encodings over rings can help us either to make this publicly verifiable or more efficient or more adapted to certain ciphertext structures. So we need to encode ciphertext in order to make them compatible with our quadratic ring program. And also new security that we have over the rings is always relying on some assumptions that are new. So these assumptions should also be kind of verified or questioned more. Okay, that was my talk. Thank you, and I'm happy to take questions.
Thank you, Anca. This was really interesting. It's really cool. I mean, I didn't realize that we could combine with FHE already to that point. So it's great to know. So we have a few questions here in the chat. Guys, feel free to unmute yourself and to show your video. It's more friendly. We're trying to emulate, this physical meetup vibe on Zoom. So just go ahead and ask your question. I think, Mami, you had one.
So last year, the cryptographers at Zcash introduced Hello2 to improve on Growth 16, and in particular avoid pairing-based cryptography, the need of a trusted setup, and power of Tau ceremony. And also with the recursive structure, even though it's not constant size, it can keep being very, very small in terms of proof. So my question is QRP like compatible with recursive SNARK like Hello2?
Yeah, that's a very good question, because the long line of recent work is working on removing the trusted setup, and the cost for that will be a logarithmic size for the proof. So bigger the computation is, which is the case for FHE computations, larger the proof will be. And how much of their techniques extend to the rings, that's, yeah, a really interesting open question, in the sense that, can we find polynomial commitments for rings without trusted setup, or can we go beyond these encodings that we have in quadratic ring programs, which is not clear. Like also all their techniques are based on hashing and completely different ways of encoding computation than the ones we are looking at for constant size SNARKs. So that's something I would like to look more into. It's I didn't spend a lot of time of thinking about.
Okay, thank you very much.
Next question. Just unmute yourself and ask it directly.
Yeah, I'm sorry, I don't know if my microphone will work correctly. So maybe, can you hear me?
Yes, it's not amazing quality, but try it. Let's try.
Okay. So I once, let me just find the question here again. Yeah, so actually I was wondering if there is a security problem when the size of the secret starts to increase. I was wondering if you have a very big secret, if this hurts the security, you see?
If the secret, no.
Sorry. If there is a relation, actually what I would like to know, if there is a relation between the size of the secret that you are trying to verify and the overall security that you are trying to provide.
Okay, yeah, I got a question.
Thank you.
So can you mute yourself, because I hear myself? Yeah, thank you. So yeah, there is no dependency in the size of the circuit and the soundness of the SNARK. So the soundness completely depends on the size of the field over which the circuit is for the field case, and in our case of the size of the exceptional set I was presenting. So in order to amplify the soundness, we can like go into extension, a Galois extension of the ring, in order to have bigger exceptional set and define the quadratic ring program there, but the secret stays the same. So the quadratic ring program will be defined over a structure like larger than the ring itself on which we do the computation, and this will allow us to have a better soundness. But the size of the secret doesn't influence at all the soundness. It does impact the proving time, of course, and the size of the common reference string as well, because the number of multiplicative gates, it's impacting the size of the setup. Does it answer your question?
Yes, thank you.
Yeah, I see a question about open source Rinocchio implementation. It doesn't exist, but if you are willing to implement these schemes, we are very happy to have people working with us and implementing it. Yeah.
Great. Do we have any other question?
Me and my
question.
Sorry, Hilder, we can barely hear you. I think we could understand your previous question because it was written, but it's a little bit difficult to understand, like your audio is muffled. So maybe ask your question in the chat and we can read it. Okay, so you said that you can verify BGV with some multiplicative level L. So you're also proving modular switching and relinearization. There's a question.
Yes, so we prove linear switching and real linearization in the sense that we design secrets over rings that model this operation. So we can translate them into secrets, and for any secret, then we know how to define the quadratic ring program. So we know how to write the secrets for this operation. For the bootstrapping, we don't, because it's so not algebraic for us, not basic arithmetics. So it's more difficult.
Okay, thank you. There's a question about whether Rinocchio is open source, as an implementation of it is open source.
Yeah, I replied to that. We don't really have one, but me and my co-authors will be really happy to have some help with this. I think we had at some point some master student that did some part of the implementation, but it's not ready at all to be open source.
Okay, great.
I actually have a question.
Yes.
So thank you for the talk. The presentation was absolutely awesome. It's also very clarifying. So I have a question related to the ring. So you can work in ZQ, where Q is whatever, not necessarily a prime number, which is like very nice. Is there, if you assume that Q is a prime power, can you actually do better? Is there a way of using this kind of structure as a way to make things more efficient or open alternative ways of doing it?
Yeah, that's a very good question. Yes, so if Q is prime, either we have better exceptional sets, so we don't need to go to a Galois extension, which makes it more efficient for us, and either we can use this other work, which is only designed for Q prime, that goes from ZQ of X over some quotient polynomial to just a secret over the field ZQ. And it's important that Q is prime because this should be a field when we translate. Yeah. So that's an alternative way for Q prime. And this work was even improved recently to better efficiency and maybe more expressive FHE operations like modulo switch. Okay.
Okay, great. Well, thank you very much, Anca. This was really super interesting. So if anybody has more questions or want to start a conversation around that, we have the Discord specifically for that, FHE.org. You can go on the website. We'll also be posting the videos online in the next few days. So Pascal, I think you just had some words about the FHE.org conference that you wanted to share as well.
Yes, we're having a conference, you all. So it's going to be by the end of May in Trondheim. So it's going to be in Norway, and it's co-located with the Eurocrypt conference. So everybody who's versed in cryptography knows Eurocrypt. For the rest of you who are maybe not so familiar with the crypto side of things, you're nonetheless very welcome to attend the FHE.org conference. So we hope to put together a very nice program, and so you cannot submit anymore because the deadline has passed already. However, there will be a lot of very nice presentations, invited talks, as well as posters, as well as demos. So so don't miss it, and try to be with us in Trondheim, Norway by the end of May. It will be awesome. And as Jeremy says, yeah, all the information is actually on FHE.org. There is a link at the top of the page, and that directly gives you information about the upcoming conference.
Awesome. Thank you, Pascal. Thank you again, Anca. That was really great. And see you all on Discord. All right. Oh, sorry, just one last word. The next meetup, I believe, is going to be about side channel attacks, if I'm not mistaken. So that should also be very interesting. Side channel attacks on TFHE specifically. All right. Have a good one, everyone.
Thank you. Bye-bye.
Bye.